right, guys. So we're going to do notes, just a piece of the gas laws for the combined gas law. So we're going to break these notes down. We're actually going to be doing notes 42 for a couple days. We're going to break each part of it down into a little piece and practice each piece along the way. So first off, it says the gas laws, the combined gas law. All of the laws concerning gases in chemistry are based upon the concept of an ideal. Oh no. It's all messed up again. Okay, there we go. Of an ideal gas. Okay? So there's like in a perfect world. So not all of this works exactly perfectly, but in an ideal world where we can control certain values, then all this math should work out. Kinetic theory assumes that the particles of an ideal gas have no volume, so they can take up an infinite amount of space. Uh-oh, this song's on. And are not attracted to each other. Let me try to write that again, look back. Attracted to each other. So we're assuming that they're not trying to bond with each other and they are taking up as much space as possible. So an ideal gas, sorry, the song is on with a 1 minute song, so I have to just let it play. But I'll read the next part. It says an ideal gas is one which follows the gas laws at all conditions of pressure and temperature. So they're keeping their pressure and temperature consistent. But basically, keep in mind, there is no such thing as an ideal gas. There just isn't. So there really isn't this perfect world gas, but that's how the mathematics work, is assuming that we can hold these things consistent. So however, real gases behave much like an ideal gas under most conditions, and many predictions about their behavior can be made. So even though it's not going to be an exact perfectness with our real gases in the real world, they should be very close. Okay. Scrolling down. So the combined gas law utilizes these three laws, these three right here, that are Charles' law, Boyle's law, and Gay-Lussac's. Now, we're only going to do Boyle's law today. That's the only one we're going to cover. I'm going to do one practice problem that's down below it. And tomorrow we'll do Charles. The next day we'll do Gay-Lussac. I'm just going to break it down piece by piece so that you can slowly learn how to put these pieces together. So Boyle's law was by Robert Boyle, who's a British chemist. The pressure and volume of gas are indirectly proportional, providing temperature remains constant. So in Boyle's law, we're saying that pressure 1 and volume 1, so the pressure the gas starts with in the size container, so that's the volume, the size it starts in, will be equal to the pressure that it ends up having and multiplied by the volume it ends up having, so the space it ends up taking. So P1 times V1, these are, since they're next to each other, they're being multiplied. So P1 times V1 equals P2 times V2. And we can use this formula to solve our problems, okay? So that's our formula that we're going to focus on. I'm going to leave it up right here. This is the combined gas law that we will get to, but I'm going to kind of leave it alone for now, and we'll save it to the end when we put all those three laws together. We're just going to do this first problem. This first one is over Boyle. So this is Boyle's law problem. Here we go. So the pressure of 5.00 liters of gas. So pressure, liters, that's a volume. Liters is a volume unit. Pressure of 5.00 liters of gas decreases. The pressure decreases from 760, so this is a pressure, to a 675 mmHg pressure. So that goes from this to this, well, that would make this P1 and make this one P2, all right? And this pressure on this liter decreases in that. So this is our original volume. So the pressure on 5 liters of gas decreases from 760 mmHg to 675 mmHg. What is the new volume of the gas? So they want to know what's the new volume of the gas, which is V2. That's our question. We're looking for V2. So if I have my formula here, P1 times V1 equals P2 times V2. I'm just going to plug the numbers in. So P2 is 760 no, it's P1, my bad. P2 was 675 mmHg equals our V1 was 5.00 liters times our P1, which was 760 mmHg. Okay, so this times this equals P2 times our missing volume that we don't know. So the way to get to the answer is I have to solve for V2. Well, in any kind of math equation, I need to get V2 by itself. How do I get this to move over here? Well, in all of these math equations, you just do the opposite of what's being done to it to move it to the other side of the equal sign. So right now, 675 mmHg is being multiplied. So to move it over to the other side, I need to divide by it, 675 mmHg. And that means I would divide it over here, divide it by 675 mmHg. So my new problem I'm going to solve is going to be 760 mmHg times 5.00 liters divided by 675 mmHg equals my V2, and that's what I'm looking for. Now, N and Hg are top and bottom of each other, so they cancel. So I will be left with the liter unit, which is the volume unit. So that's good. So I just got to put this in the calculator. So I'm going to take 760 times 5, put enter, and then divide that by 675. And I get the answer to be, for my V2, 5.63. You can still just keep those two decimal places. So 5 should be the point over here, 0.63 liters. And that's how you do it. You're just going to divide them, whatever, if you're missing this one or this one or this one or this one, if you're missing P1, V1, P2, or V2, it doesn't matter. Whichever one you're missing, you're always going to have the other three. And you're just going to divide over the one you don't have, and that will give you the answer. All right, and that is the end of notes. I will pull up the worksheet in class if you want to join, and I'll probably help start a couple of them. But other than that, that's it.